Okay, good morning. So we continue the lesson by introducing the notion of a determinant for, of course, I have written a matrix, but the matrix should be a square matrix, okay? So if you remember, we talked about the inverse of a matrix and invertibility of a matrix, but there was a very important question we didn't address so far. So how can we know that a given matrix, because usually I was a little bit abstract in my presentation in the previous chapter, but a matrix is a block of numbers. So I give you a matrix, which is a block of numbers, and I ask you if this matrix is invertible or not. We don't know that question, how to address that question yet. And even if we know that the matrix is invertible, we didn't learn in a systematic way to actually find the inverse of that matrix. So in order to be able to answer that question, it's important to know about the notion of a determinant. I really don't know what the word determinant means. Might be it determines if a matrix is invertible or not. Okay? So, yeah, we can consider that's a good definition. A determinant is you will see, it's a number that indicates if your matrix is invertible or not. But you need to, presenting the theory of determinants when you want to write it in a rigorous mathematical way becomes a little bit terrifying, but the ideas are very simple. So as you see, I can describe. Okay, so let me see how much of this definition of determinant I can read, and then I will explain what do I mean by that. So you really don't need to know the details in the definition. It's a good way to know how to calculate determinants. Okay, so here, let A be a square matrix. So it is important that I should have a square matrix. Determinant of A, so I should have written the determinants. I forgot to write. So determinant of A is denoted by this symbol, like absolute value. But whenever you see that inside the absolute value sign a matrix is there, you understand that this is denoting the determinant. Or if you want to be more explicit, you write it as det of A. So both of them are used. So the determinant of A is denoted by this symbol or that symbol, and it is defined recursively as follows. So what does it mean recursively? It means that you define it for a 1 by 1 determinant, and a 2 by 2 determinant is defined in terms of 1 by 1 determinants. 3 by 3 determinants are defined in terms of 2 by 2 determinants, and so far. So that's the meaning of defining something recursively in mathematics. By the way, instead of recursively, sometimes people call it inductively. Okay. If A is a 1 by 1 matrix whose entry is A, then determinant of A is defined to be A itself. Okay? But if A is an n by n matrix where n is greater than or equal to 2, then determinant of A is defined by this definition. So A11, which means the entry of matrix A sitting on the first row and on the first column, multiplied by C11, which I will define shortly, and plus A12 multiplied by C12, and plus up to A1n multiplied by C1n. These A's that you see here are the entries of my matrix sitting on the first row, because you see that the row index for all of them is 1, 1, 1 up to the end. And what do I mean by C1j, whatever j is from 1 to n, is minus 1 to the power of 1 plus j times the determinant of the matrix that results when the first row and the jth column of A are removed. Yeah, so this definition seems a little bit weird, but let us try to go to the board and explain it. It's a very, very simple concept. Okay, this concept is simple, but calculating determinants are tedious and boring. Okay, so this is why computers are very good in calculating these things for us. Okay, let us go to the board now. So let me just write this example, first example, as you see here. A is the matrix 1, 3, minus 4, and 5. Okay, so let me just remind you, if I give you a matrix A whose only entry is 5, if I ask you what is the determinant of A, by definition it is the number 5. I don't know, if I write A is equal to minus the square root of 2, if I ask you what is the determinant of A, the answer is minus the square root of 2. So that's definition, yes? But now let us go to a bigger matrix. This matrix is 1 by 1, then the next bigger one is 2 by 2. That's an example of that one. So what you do, you concentrate on the entries of the first row. If I want to calculate the determinant of A, what I am supposed to do? I have to take A, 1, 1. Yes, it means the entry on the first row on the first column, and multiply it by a capital C, 1, 1. And then I go to the next entry on the first row. For the time being, just concentrate on the first row of your matrix. The next one is A, 1, 2, and then multiply it by a C, 1, 2. And I will describe what do I mean by C, 1, 2. So that is the determinant of A. A11, A12 are clear. A11 is 1, A12 is 3. So there is nothing to explain there. But if I ask you what is Cij, this you need to remember. Cij is minus 1 to the power of 1 plus j, multiplied by a determinant of the matrix in which that entry, the row of that entry and the column of that entry is removed. Okay, so let me just try to do it instead of explaining it too much. So instead of A11, what do? I write 1, multiplied by, instead of C11, I write minus 1 to the power of 1 plus 1. But the determinant of which matrix? The determinant of the matrix in which this row and that column are removed. Yes? This is A11. Remove the first row and the first column. The row and the column corresponding to this entry. If you remove them, there is a 1 by 1 matrix left for you. So this becomes determinant of the matrix 5. Yes? And then I go to the next one. What is A12? A12 is the entry on the first row, second column, which is 3, multiplied by minus 1 to the power of 1 plus 2, here j is 2, multiplied by the determinant of the matrix, which occurs if I remove the column and the row corresponding to this entry. So this is here, I remove this row, I remove this column. What is left is a 1 by 1 matrix for me, so this becomes determinant of minus 4. Yes? Is that clear? And then you calculate that. But this is now clear, because if I ask you what is determinant of this matrix with one single entry, because of that definition, it is 5 itself. So let me just write them down. So this is just 1 multiplied. Minus 1 to the power of 1 plus 1. 1 plus 1 is 2, minus 1 to power 2 is positive 1. And multiplied by 5. Yes? And the next one, minus 1 to the power of 3 is negative 1, so I multiply it here. And the determinant of minus 4 is also minus 4. And if you write the answer, it's 5 plus 12, which is a 17. So the determinant of this matrix is this number 17. Yes? Is that clear? This is the way that you have to calculate the determinant of a 2 by 2 matrix. Then you realize it is extremely hard, because if you go to 3 by 3 matrix, what appears here are determinant of 2 by 2 matrices. Each one of them you have to calculate in that way. So this is why I call it tedious and sometimes A straightforward but boring calculations. Yes, whenever something becomes very straightforward for our brain, it becomes boring. Yes. So if you don't have this twist in life, probably it becomes very boring. Okay, but the good news is that at least only for 2 by 2 determinants you have a better formula. So I will use this definition and I want you to memorize that. So if I give you a 2 by 2 matrix and if I ask you to calculate the determinant of that one, the consequence of this definition is always the same. So you just multiply the entries on the main diagonal, AD, and you multiply the entries on the other diagonal, minor diagonal, and then subtract them. Okay? But of course, I have written it under the title of a remark, but I can also call it a theorem, because we can prove that this is always the case. So I want you to memorize that formula. So determinant of a 2 by 2 matrix is extremely straightforward using this formula. Let us try to motivate why this formula is correct. Why that formula is correct? Let me repeat my definition. So I give you a generic A2 by 2 matrix, and I want you to calculate the determinant of A. So what I'm supposed to do, I am supposed to go to the first row and then write the first one, but multiply it by C11. And then I go to the next one, multiply it by C12. But if I ask you what is C11, you say that it is minus 1 to the power of 1 plus 1 of determinant of which matrix? Can you tell me? I want to make sure that you understood. What should I write here? You go to this entry, it is on the first row and on the first column. You eliminate the first row and the first column. What is left? No, D. Eliminate this one and that one, so D is left. Yes? And then we go to this one, B multiplied by C12 is minus 1 to the power of 1 plus 2. Determinant of what? C. Because B is on the first row and the first column, you eliminate first row, first column, what is left for you is C. And now if I ask you to continue, minus 1 to the power of 2 is positive 1, so it becomes A. Determinant of D is simply D. But minus 1 to the power of 1 plus 2 is an odd number, so minus 1 to that power is negative. And I have B here, and I have determinant of this matrix is C. So this formula I want you to remember, at least for my lesson today, because I want to use it. And by the way, here, I haven't given you example because now you know complex numbers. You can also calculate determinants, including complex entries. So let us calculate one of them. For example, if I give you this matrix, 1 plus I, 1 minus I don't know, let me write I minus I. So this is the imaginary units, okay? So if I ask you to calculate the determinant of A, what can you calculate? By the way, now that we learned a little bit about complex numbers, now in a matrix you can have complex numbers. So all the things that we discussed so far, you can also discuss about matrices with complex numbers. Okay, so determinant of this one, according to this rule that we learned, what I'm supposed to do, I'm supposed to multiply this with that, minus, I multiply these two entries. Yes? And then let me simplify that a little bit. So I multiply this in, it becomes minus I squared. I multiply this in, there is a minus sign here, so it becomes minus I plus I squared. And I squared and I squared are gone, so the answer is just a complex number again. That's 2I. Okay, so this is the formula that we can use. By the way, I don't know, have I mentioned this? Let me see. So here, there is also another symbol for determinant. So if you see these square brackets, then that is a matrix. but sometimes you see these two parallel lines, and then I write A, B, C, D. This I don't mean the matrix, I mean the determinant. So if I ask you what this is AD minus BC. So this is also very common, and it is easy. Okay, now let us go to a more interesting problem here. This is a 3 by 3. If you learn how I calculate the determinant of this 3 by 3 matrix, probably you can generalize it yourself to higher dimensions, yes? So let us try to determine the determinant of this matrix here. Okay, so I do it patiently. I want to write all the details, but then I will tell you how to do it a little bit faster, okay? So A is this matrix. It's 1, 2, 3, 7, 0, 1, and what's the last one? 2, 9, 0. Okay, so I want to calculate the determinant of the matrix A. What I'm doing first, let us repeat everything. The first thing that I do, I go to the first column. You might say, why first column? Be patient a little bit, we will come back to that. So I go to the first column, and then I have 3 entries, 1, 2, and 3. So I write 1, but multiplied by what? C1, 1. And then I write 2, multiplied by what? C? Yeah, 1, 2. I want you to memorize the method right now. So then plus 3 multiplied by capital C, what? 1, 3. And now I go to the next step. I want to calculate C1, 1. So how should I do that? The definition is I have a factor of minus 1 to the power of what? 1 plus 1. But the determinant of which matrix? This is the first entry here. I eliminate that row, which contains this, and the column containing that. What is left for me is this block. Yes? So I need to write the determinant of that block. 0, 1, 9, 0. So you see, in order to calculate this determinant, I have to calculate 3 other determinants. That's why. But the dimension of the matrices is 1 dimension long. So then I go to the next one. So I repeat the process. I have a 2, and then I have a factor of minus 1 to which power? 1 plus 2. And then I also have a determinant. Okay, can you tell me determinant of which block? This is 2 sitting on the first row, but the second column. So you need to eliminate the first row and the second column in your head. Which block is left?
7210.
Yeah, 7210. Yes, it's simple. And then I go to the next one, plus 3, multiplied by minus 1 to the power of 1 plus 3, and then I have dot, determinant of what? Which block?
7029.
Yes, this row and this column are eliminated, 7029 is left. And then the rest of it, I hope that is simple calculation. So what I do, this is positive 1, this is 1, I multiply, it becomes 1, I don't need to write it down. But can you tell me what is the answer to this? I hope that I told you that for this lesson, at least memorize that formula.
Minus 9.
Yes, because 0 times 0 minus 1 times 9, which becomes minus 9. So the whole combination that you see here is negative 9. What is the here? You see that these powers are actually increasing by 1 unit at a time. So if this is positive, it means this is even. So it is clear the next one becomes odd, so it becomes negative. So this is negative 2. And let me multiply it by, can you do it in your head? What is this determinant now?
2.
No, minus 2. 7 times 0, 0. 1 times 2, 2. Subtract them, minus 2. So I multiply it by minus 2 here. And then I go to the next one. Again, this becomes positive because 1 plus 3 is even. So that's plus 3. And what is this determinant now? 63. And then I have to simplify that. So this becomes, if you don't mind, let me put a pair of brackets around them to make it more transparent. So this becomes minus 9 plus 4, and then 189. So this becomes 184. So this is the determinant of that one. So that's a good idea. We also check the GeoGebra to see how it works here. So we need to define my matrix. So let me call A is equal. It was curly brackets in which we have another curly bracket writing the elements of my matrix, which is 1, 2, and 3. And then go outside. I have another one, which is 7, 0, and 1. 7, 0, and 1. I have another one, which is 2, 9, and 0. Yes. And then I enter. So this defines my matrix. Am I right? Yes. Now let us see if I can calculate the determinant somehow. Yes. So the determinant of my matrix, and my matrix hopefully is A, it's 184. Yeah, so that's also good to know, to check your calculation. So what I have done is actually correct. Okay, so now that this determinant, introduction of the determinant is finished, let us go to a little bit interesting problems here. Okay, so now there is a theorem, and that is called the cofactor expansion, because these matrices are called cofactors. So what we do, it tells you it doesn't matter which row you choose to do this process. I will not prove this. This proof is technical, but I want you to know about that. So you see here, in my calculations of determinant in both these examples, I started doing the process on the first row. But this theorem guarantees that it doesn't matter if you start on the first row, second row, or the third row, and even on each column, the answers to all of these numbers become the same number. So you have degrees of freedom, which row you choose or which column to choose, and do the process. It is technical, it is not obvious at all. If I do this process, instead of doing on the first row, I do it on the second row or on the third column, the answers become the same. No, it is not clear at all, okay? Especially when the dimension of the matrix grows. This theorem, let us know about that because that's very important, but I will actually forego the proof. I will not continue to the proof. I want you to know about that. So let me read the remark now. If the first formula above is used to compute the determinant, then we say that the determinant is computed by expansion over the ith row. Okay, that's also a mistake of mine. Yes, that's correct. Because you see that I am using it on the ith row. So this is the terminology we use. If you use this formula to calculate your determinant, you say that I calculated the determinant by expansion on the ith row. And if you use this formula, you will say that I calculated the determinant by expansion on the jth column. Yes, that's the terminology I want you to know. And then the last theorem actually asserts that in computing a determinant, it does not matter which row or column one uses to expand over. The result will always be the same. Therefore, it would be easier, this is important, it would be easier to compute a determinant by expanding over a row or a column containing the maximum number of zeros, if there is any zero, yes? Because if, for example, if I started expansion on the third row, what happens? I will have something similar here, something similar there, but then this one is 0. So I don't need to bother even to think about that because that is gone. So that is the trick. If you see that there are more number of zeros on any column or any row, it is preferable to start on that row or on that column to calculate the determinant. Okay, for example, let us just do this one. This is a 4 by 4 determinant. So what does it mean? If you want to calculate this, you have to calculate 4 3 by 3 determinants. And to calculate each 3 by 3 determinant, you have to calculate 3 2 by 2 determinants. So it is a mess if you want to really calculate things. But let us try to do this. So I will go to the board. So this is the determinant I wanted to calculate. And you see that I have just written compute the following determinant by these parallel lines. This is not a matrix. When I have parallel lines, not square brackets, it means that is denoting a determinant, not a matrix. It is the determinant associated with the block of the numbers as a matrix, if you want to interpret it in that way. Okay, so let me write this in the board. So we want to calculate the determinant of this block of numbers 2, 0, 0, and 3, and then, 5. And then I have to write -1, 2, and 4, and 1, and then I have 3, 0, 0, 3, and then I have 8, 6, 0, and 0. Okay, we want to calculate this determinant. Of course, it's a good idea to start here. I think it's a little bit bad example from my side. I should have written this one first, because naturally you might start with the first one because the definition starts with the first row. But then I want to say that it's not a good idea to start here. Yes? Yeah.
Why not pick the third column?
Yeah, third column is the best one. That's the reason that I did it. So might be you start from here, you say that this is good because I have 2 zeros. But what Gustav mentioned is even better. Because if I start here, I need only to calculate one of these calculations. Okay, so but let me just do it 2 times. Might be that's my intention to make it right. So now I understand probably I did the right decision, made the right decision, because let me expand on the first one. The natural definition is to start from here. So let me put this, the question mark, so the question mark is, let me start with the first row. So what should I write? I need to write 2 times C1, 1, and then I write 0, C1, 2, and then I write 0, C1, 3, then I write 5, C1, 4. Yes? Yes? But now, of course, you don't even bother what are these numbers, because whatever they are, multiplied by 0, this becomes 0, this becomes 0. So what I bother is to calculate C11. But let me follow the definition again. What was C11? C11 is -1 always, to the power of the sum of these two indices. And then the determinant of what matrix? The determinant of the matrix in which the row and column corresponding to this is eliminated. So this is sitting on the first row and first column. If I eliminate this and that in my head, this block is left. So I write it here. So 2, 4, 1, 0, 0, 3, 6, 0, 0. Yes? So I am lucky that these are 0, because I don't need to bother about the second one and the third one, but I still need to bother about the last one. So what is the last one? So it becomes 5 times always -1 to which power? To the power of 1 plus 4, the sum of the indices. And then the determinant that is obtained by removing the column and the row corresponding to that element. So that element is on the first row and the last column. If I eliminate these two, this block is left, which is -1, 2, 4, and 3, 0, 0, and then I have 8, 6, and 0. Now, you assume that if you have started the same process on the second row, according to the theorem, it definitely works, but you have to calculate 2 more terms. So this is much much more efficient if I do it in that way. It's also a good exercise in programming to write a code that calculates the determinant of any n by n matrix. Okay, so if we want to continue, so let me make this a little bit simple. This part is how much? This is minus 1 to power 2. 2 is even, so it's 1 times 2. But I have a 3 by 3 determinant to calculate. I have to do the same process again. So this becomes 2. I open a big bracket here. I want to do the calculation for this determinant inside here. And then I will jump to the next one. So, okay, so what should I do? Which one do you prefer? Of course, I can expand on the first row, but that's not a good idea because all the terms will survive here. Which one you prefer? Let us this time, for example, jump to the second row. Okay, if I jump to the second row, what should I write? Can you tell me? I should write 0 multiplied by c what? I'm expanding on the second row, but 0 is on the second row first column. 2, 1. So this is c 2, 1. Of course, it doesn't matter which one because it is multiplied by 0, but let us do it properly. And then I go to the next one, which is, the next entry is 0 multiplied by c 2, 2. And then I go to the next one, which is 3 multiplied by c 2, 3. But for which determinant, it's probably that for that determinant. Okay. And then plus or minus, which one do you think it is? It's minus 1 to the power of 1 plus 4, which is 5. It's an odd number, so it becomes minus 5. So I would write minus 5 here, and then I'll open another big bracket, and then I will calculate C's on the one. But these are two different matrices. If I call them capital C, let me call them, I don't know, capital C prime, showing that they are different. So which one you prefer to act here?
Second row.
Second row. It is again possible to do it on second row, but for making it a little bit, so to practice more, let us do it on the third column. Okay, I'm just for practicing different situation. That is completely okay if you, even if it's okay if you start there, but that is not efficient. So let me just expand on the third column this time. So what should I write? I should write 4 C, let me write C prime because it's a different matrix. I want to differentiate between these. So what should I write here? I should write 4 is on the first row and the third column. First row, third column. And then, of course, I go to the next one below it, which is 0, C prime of what?
2,
2,
3.
3. And finally, again, 0, C prime of what? 3, 3. Yes? Okay, so you see that the more zeros we have, the easier the calculation becomes, yes? And here we don't need to calculate this, we don't need to calculate that. Okay, 2 times 3 is 6, but I have 2 and 3, so it becomes minus 1 to the power of 2 plus 3. Then I am waiting for you. So what should I write here? Remember, this is just calculating this one. Where is 2, 3? The second row, the third column, the second row, and the third column. You need to eliminate in your head or whatever the second row and third column. Which block is left?
2, 4.
2, 4, 6, 0. Yes? So I need to write 2, 6, 4, 0. Am I right?
No, 2, 4, 6, 0.
Ah, okay, 2, 4 here.
In this case, it doesn't matter.
Yeah, 2, 4, 6, 0, but it's better to be careful. That's correct. And then I go here, minus 5 times 4 is minus 20. And then I need to do the calculation here. The first row and third column. First row and third column, you eliminate them. What is left? 3086. So this becomes 3086. Yes?
So you can have the -1.
Yeah, I have to write that -1 to the power of 1 plus 3. But of course it doesn't matter, but let us write it properly. Okay, but this is a 2 by 2. I gave you the rule. I use the same idea. It is on the board. I told you memorize that for this lesson. If I have a 2 by 2 matrix, its determinant, if you follow the process, it will always give rise to AD minus BC. So what's the answer here? So this is -1 times that's -6, and then this is 2 times 0, 0, and then minus 24. And then this is -1 to power 4, which is positive. I have a -20 here. And then if I do this in my head, it is 18 minus 0. So that is just 18. Okay, and then if I calculate this, this is 144. And this is minus what? 360. So if I calculate that, it becomes what? 6, 2, and 2 minus, yes? Minus 226. Or 16, yes, sorry. It's minus 216. Okay, so also a good idea to check the calculation using GeoGebra.
For how long?
It doesn't matter. Not that much when I switch to GeoGebra. Okay. Okay, I want to wait for you because now you learn the new. I didn't say you why this is useful, but just let me repeat that. You will see that determinant determines if a given matrix is invertible or not. Okay? How? If it is not zero. The criterion is actually extremely simple. If the determinant that you calculate is not zero, it guarantees that the matrix corresponding to that determinant is an invertible. But still there is one question. Okay, if I know it's invertible, how should I compute its inverse? Okay, we will come back to this question a little bit later after I talk to you about the theory of determinants a little bit more. Okay. So I want to wait for you. Determine x from the following equality. So that is a determinant equation if you want. I have an unknown, I am looking for it. By the way, you can calculate both of them. I want to wait for you to solve example 2.8 and 2.9 for me, okay? Okay, so let us solve the problems. Do you have the answer for the first one? No? It shouldn't be hard, but let me just do the calculation. So you calculate the left determinant. So let us make it easier to write. So the left-hand side, of course, this is not an identity that I want to start from left going to the right, but because it becomes messy, so let me calculate the left-hand side and the right-hand side and then equate them, yes? So the left-hand side is equal to what? X, so let me don't write the original form itself. So you know that this is a 2 by 2 determinant, so I take that entry and that entry. These are the entries on the main diagonal. I multiply them. I take the entries on the minor diagonal, I multiply them, and then I subtract. Yes? So that's the 2 by 2, so it's straightforward. Let's just expand that a little bit. This becomes x minus x squared, positive 3. So that's the answer to the left side. Yes. And for the right side, you have to work a little bit harder. So the right side, and then hopefully you agree with me, the first row is very natural here to start with as usual. So what I do, by the way, I do it quicker in this way. So I take this 1, 1. So I will first keep track of that -1 to some power factor. Yes, so I would say that which entry is this? First I decide to on which row or column I want to expand. So this is my decision to do it on the first row. Then I come here and ask myself, what is the number of the entry here? It's 1, 1. 1 and 1 added, it becomes even. So I can put a plus sign on top to remember that, because minus 1 to power even becomes plus. And whenever I know this, I don't even need to calculate the next one. The next one is negative, the next one is also positive. So you can put something like that on top of my head. Okay? So when I want to bring one down, I bring it with considering this sign together. So it becomes positive. And then in my head, I take this and that off. So what is left? I put a determinant x minus 6, 3x minus 5. So that's easier. And then I go to the next one. Of course, here it is 0. But when I want to bring 0 down, I also consider this sign here. So it becomes negative 0. Of course, it doesn't matter. But let me write everything here. Then I eliminate this column and that row. This block 2 minus 6. And then 1x minus 5 is left, which of course, it doesn't play any role because 0 is here. And then the next one is negative. The top sign is positive, so in principle, I have to bring minus 3 down, and then I eliminate this one and that one, so this is 2x, 1, 3. Yes? That's the same thing essentially, but I'm trying to do it a little bit faster. Okay, then what happens here? I don't need to consider 1 multiplied, so I just consider this one. So x times that minus this times that. And then this is totally 0. I don't need to consider that one. Then I have a minus 3. And then 2 times 3 is 6. 1 times x is x, and subtract. And then if I simplify this a little bit, so this becomes what? X squared minus 5x. And this is positive 18. And this is negative 18 plus 3x. And this positive 18 and negative 18 are gone, so this becomes x squared minus 2x. So this is the left-hand side, and that's the right-hand side. But I want to solve an equation in which the left-hand side is supposed to be equal to the right-hand side. So let me write it here. So the left-hand side is this, is equal to this one. And this is a quadratic equation, so that's a Math 2C problem, yes? So I move this to the other side, it becomes 2x squared. I move this one, minus 3x, and then I have minus 3 equals to 0. Do you agree? And then let us calculate this. So this is simple, yes? X is equal to minus b plus or minus the square root of this number to power 2 minus 4 times this, that, which becomes what? Plus 24, and then divided by 4. Am I right? So this becomes x is equal to 3 plus or minus the square root of 33 divided by 4, and that's the answer. Okay, that's also a good idea if I check my calculation to see that if it's also working using GeoGebra here. Okay, so my matrix here, so let me just introduce it without names. So the matrix on the right is 1, 0, minus 3. And then, okay, I have to put another curly brackets around that one as well. Yes. So what was that? It was 1. And then I go here. It is 2x. 2 and x, and the next entry is minus 6, and then I go to the next one. What is that? 1, 3, x minus 5 as a whole, yes. And let me just do it like this. So I would write determinant, yes, if it works like that, hopefully. No. Might be that's my mistake, because this GeoGebra acts a little bit weird.
I think there was an extra pair of brackets.
Was it?
I think so.
Okay, let me just do it once more. Let me give it a name. Let me give it name M. I want to reserve A for the later time. Okay, so what was that? Can you read it again to me, Gustav, please? 1,
0,
0,
minus 3,
minus 3,
2,
And then I go to the next row, 2,
X
x
minus 6.
minus 6. And then I go to the next row, 1, 3,
X minus 5.
x minus 5, yes. And then this is this, but let me write determinant of m now. And then let me write my matrix M. No, it cannot calculate for some reason.
It's because of X.
Yeah, because of X, but it shouldn't be that hard. Because GeoGebra knows how to manipulate variables. Anyway, we can, I'm sure that there is a way to fix this, hopefully. Okay, but let us leave it for the time being. Okay, and come back to that question. So I have given you a matrix, and then I'm asking you just calculate the determinant of this combination. First of all, you shouldn't invent rules. So you cannot say, I can say determinant of that one plus the determinant of that one. It might be right or might be wrong at this stage. If you want to use that, you have to prove the theorem. But let me tell you, this is not correct. So the determinant of the sum of two matrices, determinant is not a linear function in this sense. So it is not the case that if you add first and then take the determinant, it becomes the same if you take the determinant first and then add. In general, this is not true. So here, you have to do a trivial, tedious calculation. You have to calculate A transpose. You calculate A transpose A, add them, it becomes a matrix, and then take the determinant. So that's the only thing we can do. And then hopefully we can check with GeoGebra again, because that's a numerical calculation. So what I do, I calculate A transpose first. So what I write, I just copy and paste A itself. Well, hopefully you remember. How should I write the transpose? I need to interchange the rows and columns. So this is the first row, I put it as the first column. This is the second row, I put it as the second column. And this I put it as the third column. And then I do the calculation. So this row multiplied here, 1, 4, and 1, 6. And then you take it here, it is 1. And then it is 1 and 1, 2. And this is just 1, 1, 1. And this is, adding these two is 2, 1, and 2. Yes, is that your answer as well? Okay. And then of course I have to calculate A transpose A, which in general is not the same thing, yes? So this time I write the transpose first, and then multiply it by my matrix. Yeah, please watch my calculations. If I'm doing something wrong, please let me know. I take this one here, it is 2, and that is 2 again, and that is 2. And then this is 2, 4, and 2, and that is the 2, and 2, and 3. Yes? And then I have to add them up. So if I add them up, so A transpose plus A transpose A becomes equal to my new matrix. So let me add the results. So 2 and 6 becomes 8, and then 3 and 4, and the next one is 3, 5 and 3, and the next one finally is 4, 3 and 5. Yes, am I right? Did you get the same thing? Okay, and then I calculate its determinant. Now, there is no other way, so let me just do this. So the calculation is the determinant of this combination. And let me just do it as I told you. So there is no preference here, so let us just do expanded on the first row. But the first row is 1, 1. 1 plus 1 is 2. 2 is even, so it gives me a plus sign here. When this is a plus sign, it is clear the next one is 1, 2, it becomes odd. So it gives me a negative sign, the next one gives me a plus. Okay? Okay, so then what happens? When I want to bring 8 down, I consider this sign on top here, so I bring it positive 8. And then I need to eliminate these two, and then what I get is 5, 3, 3, 5. And then I go to the next one. The next one is positive 3, but because of that negative sign, I put negative 3. And then what I do, I eliminate this column and that row. So 3, 3, 4, 5 is left. And then finally I go here, 4 is positive, this sign is also positive, so I bring positive 4 down, and then I remove these two, 3, 5, 4, 3 is left. Yes, is that right? And then I calculate them. So this becomes 8, this times that is 25, this times that is 9, subtract them. This times that is 15, this times that is 12, subtract them. And then this times that is 9, this times that is minus 20. Yes. So this is just how much? 16, yes? So 16 times 8 is what? 112. Yes. 16 times 8. So this is 80 and this is 48. No.
Isn't it 128?
128, yeah, sorry. And this is minus 9. And this is minus 11, so it's minus 44. So what is that number then? So this is 48. Yes, 84. So it's 75, am I right? Okay. So the number seems to be 75. And let me see if GeoGebra is capable of putting everything in one go here. I think there is also a transpose here. So let me put my matrix there. So my matrix is what? Is a 1, 2, 1. And then I have another row, which is a 0 and 0 and 1. And then I have another one, which is 1, 0 and 1. 1, 0 and 1. Yes? Okay, this is the introduction of my matrix, but I want to calculate determinant. But what is my matrix? Let us see if it is capable of doing that. I have A times A transpose, yes? So I would say A. Let me put multiplication sign. And then I think transpose is also like this, yes? So transpose of my matrix, which is A. Yes? And then plus transpose this time of my matrix, which is A, and then I put multiplication sign, and then my matrix, it's 75. So I don't know, it's a little bit weird, it couldn't calculate that determinant with X there. But anyway, that's correct. So you can use these, it's better to learn the application here, very good. Okay. One thing I just want to finish the lesson. So at the next lesson, you see that calculating determinant could be tedious and messy. So it is good to have some theorems in hand so that if they are applicable, we can calculate our determinant faster. For example, this theorem that I have mentioned here, if a square matrix contains a 0 row, by a 0 row I mean a row containing all zeros, nothing else. Or a 0 column, do you agree that its determinant becomes 0? Yes, because if I have a 0 row, it means that in order to expand my determinant, I will go on that row and do a start expansion. And all these coefficients that coming first are 0, so it becomes 0. So if you have a determinant, for example, like this, hopefully I have given you an example. So you really don't need to calculate this, because you see that you have a full 0 row, so the answer to this determinant is 0, and if I ask you what is this determinant, again you have a 0 column, so this becomes 0. Okay, but then I will talk a little bit about these kind of theorems coming next session. So we will learn a little bit about some important theorems related to calculating determinants. Any questions? Okay, thank you.